The $10 billion telescope. How powerful is it? How does it transmit images from 10 billion light years away to us? The answer lies in its mid-infrared camera, MIRI. When a beam of light enters the camera, a series of complex lenses and filters separate the light into different wavelengths, adjusting their size and guiding them to the sensor. With this camera, the telescope can see distant stars and galaxies invisible to the human eye. But all this is possible only if the camera is cooled to -267 degrees Celsius, just 6 degrees above absolute zero. Incredibly, this cooling is achieved through sound. Hence, MIRI is also known as the cryocooler. The genius behind this technology is remarkable. So, why does MIRI need such a low temperature? And how is it cooled using sound? First, we need to understand that the telescope primarily observes infrared light. As light travels through space, its wavelength stretches with distance. If a galaxy is too far away, the light stretches so much that it becomes invisible by the time it reaches Earth. This means our observation range is physically limited. MIRI's sensor, made of deep silicon, can detect this highly stretched infrared light. It works similarly to a regular camera, converting photons into electrical signals. The main difference is that the telescope needs to detect faint infrared signals, requiring MIRI's sensor to be extremely sensitive. However, increased sensitivity also increases noise. For example, when taking a photo with a phone, the sensor detects not only the intended object, but also a lot of light reflections, invisible to the naked eye, creating noise. If the target signal is bright enough, it stands out against the noise. But for faint infrared light from distant galaxies, increasing sensor sensitivity also significantly increases noise. Every object in the universe emits heat, some in the form of light. Most objects are not hot enough to emit visible light, but they emit a lot of infrared light. The hotter the object, the more infrared light it emits. This is the principle of thermal imaging. Unfortunately, the telescope at the second Lagrange point emits a lot of infrared light itself, which would overwhelm its sensor. To limit the infrared light emitted by the telescope, scientists came up with a brilliant solution, cooling the camera to -234 degrees Celsius. They placed it behind 5 large sun shields to block most of the heat, cooling the camera to around -234 degrees Celsius. But MIRI's sensor is so sensitive that atomic vibrations inside it create a lot of noise, misrecording photon positions. Since temperature measures atomic vibration speed, further cooling is needed to reduce vibrations and noise. Thus, the sensor must be cooled to -267 degrees Celsius, near absolute zero, to nearly stop atomic vibrations and achieve the desired image. To achieve this, scientists installed a pulse tube device at the telescope's base. 2 pistons move back and forth, compressing helium in the pulse tube. The piston's movement creates vibrations, which must be precisely controlled to cancel each other out. Amazingly, the pistons move very fast, like a speaker, producing a low-frequency sound wave at 30 Hz. The sound wave travels along the tube, creating a high-pressure zone at the end, then rebounds, creating a low-pressure zone, and is compressed again. The secret lies here. If the next sound wave is emitted, just as the previous one returns, the frequencies match, creating a standing wave with fixed high and low pressure zones. Increasing the frequency threefold creates multiple high and low pressure zones. Since temperature and pressure are related, multiple hot and cold zones appear. But this doesn't change the overall temperature. The heat must be extracted to lower the temperature. Scientists added 3 layers of thin metal plates as heat exchangers, placed at alternating hot and cold spots. This extracts heat and releases it, cooling the temperature from 27 degrees Celsius to -256 degrees Celsius. To truly cool the sensor, another set of pistons compresses helium in an independent circuit, which passes through the pulse tube's cold part, cooling the helium to -256 degrees Celsius. The helium then travels through a 10-meter-long thin tube to the cold head, but minus 256 degrees Celsius is not enough. Another heat exchanger and a tiny orifice are installed inside. When helium passes through the orifice, the Thomson effect occurs. The gas compresses and rapidly expands on the other side, lowering the pressure and cooling the gas quickly. This is why exhaling feels warm, but blowing feels cool. This key action cools the helium to minus 267 degrees Celsius, connecting to MIRI's sensor's copper plate, providing the needed low temperature. The helium then returns to the telescope, repeating the cycle. This is the key to the telescope's ability to see billions of years away. It's surprising that sound can be used for cooling. Such a perfect design is thanks to the scientists' great efforts. The telescope has been working in space for over 2 years, capturing cosmic wonders that continually refresh our understanding and unveiled the early universe. In the future, it will lead us through time and space, guiding us in the cold, silent universe.